All right, so we are going to work today on energy and work and some power, but mainly energy. And there are a couple kinds of energy. I think you learned in middle school about potential energy versus kinetic energy.
Mm-hmm.
And just to review a little bit, potential energy is stored energy. And you already know about a lot of potential energy, but he might not have told you this, but there are three types of stored energy, three types of potential energy. There's elastic potential energy, and that's like a rubber band that's stretched, and it's ready to pounce. And by the way, when it's stored energy, it means it can become motion.
Okay.
Right? Like it's not motion yet, but it's stored and it could become motion if you converted it.
Okay.
And then the motion energy is going to be kinetic, but the potential is when it's stored. So picture a rubber band that's stretched, right? And it could become motion if you let go of it, or a spring that's either compressed or stretched, etc. So these are like elastic potential energy.
Okay.
The second type is chemical potential energy. And chemical potential energy is stored in food, because think about it, the food that you eat could become motion after you get the energy out of it. Gasoline for the car can become motion, or batteries, which have electrical potential energy, and they can make things move easily. The energy stored in batteries can make lots of things move. So chemical potential energy in food, gasoline, and batteries. There's just three examples. And then the third type is the one you're going to use the most in this chapter, and that's called gravitational potential energy. Now for gravitational potential energy, I'm going to say GPE.
Okay.
Now gravitational potential energy is when something is up high and it's ready to fall. So I'm just going to say ready to fall. Like when you're up on a ladder and you could fall off, you've got gravitational potential energy, and when you think about it, that could become motion if you fell.
Okay.
So those are the three types of potential energy. Now later I'm going to teach you the equation for the springs, the elastic potential energy. The springs have an equation, but we'll get to that later. First, we're going to start with the one that's most common, and that's gravitational potential energy. So potential energy can be converted or transformed into kinetic energy, and kinetic energy is energy of motion.
Okay.
So kinetic energy is when it's in motion, and potential energy can be converted into kinetic energy. You've probably heard this already, but there's the law of conservation of energy.
Mhm.
And the law of conservation of energy means that in a transformation or a conversion of energy, so let's say in an energy conversion, where one kind of energy converts into another, the total amount of energy before the conversion, the total amount of energy before the conversion equals the total amount after. And so you're not losing, that says total amount of energy after. I'm writing too fast. So you don't lose any energy just because it's converted from one form to another. So let me show you an example. If you have somebody standing on top of a ladder, and let's say that they have, let's say 50 joules of gravitational potential energy, and I'll tell you how to calculate that in a minute. So if they have 50 joules of gravitational potential energy, when they jump off, it's going to convert into 50 joules of kinetic energy.
Okay.
So it's not like the amounts are different when they convert. It's going to fully convert. Now halfway down, this is the cool thing. halfway down, it's 25 and 25.
Okay.
So it's 25 joules of potential energy and 25 joules of kinetic energy when it's halfway. So it's converting as it's falling. The energy is converting. How do you know how to calculate these things? So gravitational potential energy depends on the height of the object and the mass. Basically the height and the weight. Oops, I'm running out of room. So it depends on how heavy you are when you're up high and also how high you are. So do you remember the weight is mg?
Yes.
So the weight is mg, and then you multiply that by height. So that is the simple formula for gravitational potential energy, the weight times the height.
Okay.
So usually in these problems, they're not going to give you the weight, they're going to give you the mass. And you just have to remember to multiply the kilograms, the mass in kilograms, by 9.80 meters per second squared, which is g. So the weight, as you know, equals mass times 9.80.
Yeah, okay.
Okay.
I got that part.
You got that. Good. The kinetic energy formula is a fun one. The kinetic energy is 1/2 mv squared. Now, do you remember kinetic energy is energy of motion?
Mhm.
So motion means it's moving, and v is the velocity. M is the mass, and the v is the velocity or the speed of the object in meters per second.
Got it.
Don't forget to square it. So it's mv squared. Okay?
Okay.
So KE, we like to say KE equals 1/2 mv squared. And this is a formula. You know how sometimes your teachers give you a formula at the top of your test, sometimes to help you remember?
Mhm.
After you do this chapter, most teachers expect you to remember this one without them ever telling you again, because it's kind of like F equals ma. It's one of those formulas that teachers think, oh, you might use this again in like chapter 11 and chapter 16, and they're not going to remind you of it. They just expect you to know kinetic energy equals 1/2 mv squared. So sort of get really comfortable with 1/2 mv squared.
Okay.
Okay. So falling off of the ladder, we could do a conversion of energy where we say his potential energy turns into his kinetic energy, and if we knew his height and his mass, like I'll give you some numbers, we could figure out his velocity once he gets to the bottom.
Mhm.
Do you agree that if somebody's on the ground, oh, by the way, the ground level, we always consider the ground level to be 0 height, even though you might be standing on a mountain and you're not at sea level, and your height is not technically 0 because you're not way down at sea level. Like you're really up high when you're on a mountain. But we still consider standing on the ground to be a height of 0 when we're doing these problems.
Okay.
So whenever something falls down and it actually makes it all the way down, or think about this, when you're doing a pendulum problem and it's swinging back and forth, when the pendulum is at the very bottom, like let me draw over to the left really quick. I'm going to draw a pendulum, and it's going to like swing down to the bottom and then swing over here. So it's going to swing back and forth, right?
Mhm.
It's when it's at the bottom of its pathway right here,
Yeah.
this is going to be considered height equals 0 meters.
Okay.
So the bottom of the pendulum is height equals 0, or the ground is height equals 0. So you figure out in each problem that, you know, what the 0, it's called ground 0 whenever you figure out, okay, that's going to be the 0 mark for this problem.
Okay.
So when he falls off the ladder and you're figuring out the height, you want to know the height from the ground level up to where he's standing, and that's going to be the height that you use when you do MGH. So let's say I make up some numbers. Let's say that this guy is 70 kilograms. That's his mass. And let's say that the ladder is 10 meters high. The problem is just going to say, what's the velocity when he hits the ground? So let's say his velocity is the question mark before he hits the ground. So we'll say at the bottom or at the ground, right before he hits. Now a lot of kids are like, oh, well, when he hits the ground, his velocity is going to be 0. And that every teacher says, no, I mean the velocity right before he hits the ground. I know that after he hits the ground, he's going to stop. But you're going to calculate the velocity right before he hits the ground. Like, how fast does he get going? So what you do is you say, okay, potential energy is becoming kinetic energy. And at the top of the ladder, before he jumps, would you agree that at the top he's got, let me try this gray, he's got all potential energy at the top, and he's got no kinetic energy yet? Okay. So hang on while I erase my pendulum really quick so that I can draw something right here without turning the page. Okay. So we're saying that at the top he has all potential energy and he has no kinetic energy at the top. Halfway down it's half and half, but down at the bottom, do you agree he's got no potential energy on the ground and he's got all kinetic energy right before he hits the ground? So it converted all into kinetic.
Yes.
And halfway it's half and half along the pathway.
Yes.
Okay. So we're going to say at the top his gravitational potential energy is going to be everything he has at the top and before he falls, and that's going to equal the kinetic energy after he falls. And that's because of the law of conservation of energy that says that the energy before a conversion is equal to the energy after the conversion. So that's where this equation comes from. The total energy before, we knew that in his case it was all gravitational. Now, in later problems, you're going to have somebody who's up high and they're already moving. So at the beginning you'll have gravitational and kinetic. But right now we're having somebody who's at the top not moving, so it's only gravitational potential energy at first. And afterwards he's going to be all the way down flat on the ground at 0 height, and that's going to be all kinetic right before he lands. So it's really easy. All you do is the gravitational potential energy equation is mgh, and then you do mgh equals 1/2 mv squared. Now notice that there's the same mass on both sides. We could plug in the 70 kilograms, couldn't we?
Yeah.
But watch this. Can't we cancel mass on both sides? You don't even need, they didn't even need to tell you his mass. All you needed was how high he was to figure out his velocity at the bottom. So you can rearrange this equation and end up with a really simple shortcut when somebody's falling, and you can use this with pendulums too, that the velocity at the bottom equals the square root of 2gh, and the h is the height at the top. And that was just algebra that I multiplied both sides by 2, and then I took the square root of both sides to get rid of the v squared.
Got it.
So this is a good shortcut when you need to know the velocity at the bottom and they give you the height at the top. So I'm going to plug in 10 meters for the height, 9.8 for g, 10 times 9.8 times 2, and then I'm going to take the square root of that. And the velocity is 14. Wow, he got going pretty fast. Poor guy. So he's 14 meters per second right before he hits the ground, when he gets to the 0 height mark. Do you like it?
Yeah.
This is a really good conversion of gravitational potential energy right to kinetic energy.
Okay.
All right, you ready to do a little bit different? We can do, we could either do a pendulum, or we could do something at an angle, or we could do a spring. Let's do a spring next.
Okay.
All right. There's lots of different ways we could go, but let's do a spring. So the potential energy stored in a spring. This is the elastic potential energy. Now the spring could be squashed or compressed. It could be squashed or stretched. So when they talk about equilibrium of a spring, equilibrium is considered the relaxed position of the spring. So if you have a spring that's like this, it could be squashed by a certain amount, or it could be stretched by a certain amount. And either way, if you squash it or you stretch it, it's going to resist and push back. Now the force of the spring pushing back or pulling is going to be negative kx. This is called Hooke's law. Okay, do you agree? I've been saying okay a lot. I got to stop saying okay. It's a bad habit.
It's all right.
That's Hooke's law right there. The force of the spring, now the spring is going to push or pull. Do you agree that if I push to the right, so if I push the spring in this way, and x is the difference, is how far I push it. So we'll say by x meters. The spring is going to push back this way. Do you agree? Because it always pushes against whatever way you pull or push, right?
Mm-hmm.
That's why there's a negative right here, because the force is always going to be opposite the direction that you push or pull. So x will be one direction, and the force of the spring pulling or pushing back is going to be the opposite direction from x. That's why this guy Hooke, decided, I need a negative in that equation, because in physics, negative means opposite direction. It doesn't mean less than 0. It just means the opposite direction. So the force is going to be negative if x is positive, and the force is going to be positive if x is negative. All that means is they're in opposite directions.
Okay, got it.
All right. So the K right here, the K in this equation is the spring constant. I'm going to have to write it down below. The teacher will usually give you the spring constant for each spring. All it means is how strong, how thick or how thin is that spring? How strong or weak is that spring?
Okay.
If you have a really fat, strong spring, like something in a box spring mattress, and it's a really strong spring, that's going to have a high spring constant. And if you have a tiny little slinky like a toy, that's going to have a really small spring constant. So the spring constant just tells how strong the spring is. And you can imagine if K is high in this equation, then the more you push on the spring, the greater the force of the spring pushing back on you.
Okay.
Because K is high, the spring is strong. So this is just, so far, all we've done is the force of a spring pulling or pushing back on you. And remember, if you pull on the spring, it's going to pull back. If you push on the spring, it's going to push back. And x is just how far you go. And they're usually, your teacher's going to give you centimeters. They love to do that, or millimeters. And they're going to expect you to know how to convert from centimeters to millimeters. So really quickly, centimeters to meters. So if they say 5 centimeters, it's just like 5 cents. Think of centi and cents in the dollar. So 5 centimeters, however you would show 5 cents.
Okay.
So it's 0.05 meters. So it's just exactly like cents in the dollar.
Okay.
And they're always going to try to trick you like that. All right. So we just talked about the force. All of this is the force that a spring uses to pull or push back on you. However, we haven't yet talked about the energy stored in a spring that's been stretched or squashed. The potential energy that's stored in a spring that's been squashed or stretched is this equation. 1/2 kx squared. It kind of reminds me of this. Look at the very, very bottom. Do you remember kinetic energy of motion is 1/2 mv squared?
Yeah.
The potential energy in a spring looks kind of the same, 1/2 kx squared. Not the same, but a little bit similar in the
Just the
form.
K
Yeah.
and the X. I guess it's just like different variables.
Yeah, different variables, but the 1/2 and the squared are the same.
Okay.
Okay, that's the potential energy stored in a spring. So you just multiply 1/2 by the spring constant, and x again is however far you've squashed the spring from its equilibrium position.
Okay.
So now I'm going to give you a little bit of a harder problem for fun. Okay.
Okay.
This, for some reason, they love to have this block on a spring, even though in real life you would never have like a block sitting on a spring. But I guess you could in some kind of a machine, right? All right,
Yeah.
so let's say that this is equilibrium, and let's say that this block is 8 kilograms, and let's say that the spring is stretched out this way by 15 centimeters.
Okay.
So that's x. That's how far you've stretched it. All right? You're going to love this, but how fast is the block moving? So it's going to be stretched 15 centimeters and then let go. You're going to let it go, and it's going to go back in.
Okay.
You got it? Okay. How fast is the block moving? A, at equilibrium, when it gets back to the relaxed position of the spring. Now the thing is, the block's going to go past equilibrium because it's going to have that kinetic energy, and it's going to be moving, and it's going to have that kinetic energy that pushes the spring back in even further. Like if there were no friction, it would go in 15 centimeters, and then it would come back out 15 centimeters, and then it would go back in 15 centimeters. And so it would keep going back and forth and back and forth. But at equilibrium, how fast is the block moving? And part B, as it passes the 7.5 centimeter mark, in other words, halfway in.
Okay.
All right, so let's try the first one at equilibrium. Oh, I like orange. I'm going to go for some orange. It's going to look like Halloween with the gray and the orange. I'll go for pink. All right. So the energy before equals the energy after. That's conservation of energy, right?
Mhm.
So let's talk about beforehand. Before it's released, when you stretch it out, you could either have potential energy of a spring, you could have gravitational potential energy, and you could have kinetic energy. And then afterward, we're going to say potential energy of the spring, gravitational potential energy, and kinetic energy. This is what you're going to use when the problems get complicated, but not all of these are going to apply. Does the spring have any gravitational potential energy? Is it up high off the ground?
No.
Is the block. So the block's not going to have gravitational potential energy before or after. So that's not going to apply, okay? Before we let go of it, does it have any kinetic energy?
No.
No. So this is going to be, we're going to go for part A at equilibrium. Okay? So this is before you let it go, and then this is going to be at equilibrium. All right. Okay. So kinetic energy, none before. When it's passing through equilibrium, does it have kinetic energy?
Yeah.
It does. So we'll keep that one. When it's passing through equilibrium, remember that equilibrium is the spring's relaxed position. Does the spring have any potential energy at equilibrium?
So, like, you're saying equilibrium is like,
it's that position.
It would have potential energy because it's like stopped in like a position because it's like it's equilibrium.
Okay, equilibrium is going to be the length of the spring when it's relaxed. So equilibrium means, by definition, x equals 0, because it's at equilibrium, that's the relaxed position of the spring. It's not squashed or compressed or stretched at all.
So it would have potential energy.
Okay, would it? Because think about potential energy as 1/2 kx squared. And at equilibrium, if x equals 0 at equilibrium, then there's no potential energy at equilibrium because there's no force. The spring is not stretched or compressed at equilibrium.
But it's not like moving.
It is? Okay, cool. So picture this block going back and forth with this spring, right?
Mhm.
So pretend I drew it, the way I drew it, the spring is actually relaxed. Like that's its comfortable position if it's sitting still.
Okay.
If I stretch it this way, it's going to move, right?
Mhm.
And the spring is going to stretch and you're going to have x that way, a certain amount, right? It's going to come back and then it's going to pass equilibrium and it's going to go in past equilibrium because it's going to go boing, boing, boing. So it's going to go, you see how it's going to pass through equilibrium and then go.
Yeah, but it's still like, okay.
But right at that equilibrium mark, x is 0. Right at equilibrium, x is 0. And right there, the spring, right as it passes through equilibrium, which is the place where it started, there is no stretching or compressing of the spring. It's passing through the point where it used to be relaxed. And x is 0 right there. So there's no, even though the block is moving, the spring at that exact moment is not pulling or pushing at all.
Okay.
Now when the block is pulled out, the spring is pulling back. When the block moves in and squashes the spring is pushing out. But right at equilibrium, it's right between pulling and pushing and it's doing nothing.
Okay.
Does that really make sense?
Mhm.
So right at equilibrium, down to our equation at the bottom, right at equilibrium, the potential energy of the spring, which is like the pulling and the pushing energy of the spring, that's 0.
Okay.
Does that really make sense? Because right at that place, the spring is not pulling or pushing. Now, as soon as it passes equilibrium, yes, the spring is going to be pushing again. Yeah, it starts pulling or pushing.
Yeah, I get it.
Okay, good. So we have a pretty easy equation right now that we've got that the potential energy of the spring beforehand, which is going to be 1/2 kx squared beforehand, is going to equal the kinetic energy of the block after it comes back, which is 1/2 mv squared.
Okay.
Are you cool about that? So this is potential energy of the spring as it's stretched, and this is the kinetic energy of the box at equilibrium as it's coming back. All right. So we're going to start plugging things in. I don't think I gave you a spring constant, and I should have, but that was just me being like a teacher who's making things up as I go along. Let's say that I give you K equals 19 newtons per meter.
Okay.
And it's probably too low, 119 newtons per meter. All right, so let's do 1/2 times 119 times, and what number do we put in here for the x? How far was it stretched?
It was 15 centimeters.
Yes, so what number, can we put 15 in there?
No, because, wait, it was stretched, so do you have to do half of it?
No, you're going to do meters because x has to be in meters.
Oh, okay.
So they're always going to try to trick you by giving it to you and not in meters. What is 15 centimeters?
Like 15 cents, so it would be 0.15.
That's right. It's just like 15 cents in the dollar. So 0.15 meters. So we're going to plug in 0.15 and then square that.
Okay.
Because x has to be in meters. And then we go 1/2, and then we do the mass of the block, which luckily they gave it to us. And then they're asking for the velocity, and all we have is one unknown.
Okay.
So we can get rid of the 1/2, luckily, because they're on both sides. And we can do the algebra. We can pull out a calculator and do 119 times 0.15 squared. And then we're going to divide that by 8, and then we'll take the square root. So I get a velocity of 0.579 or 0.58.
Okay.
Okay, so the velocity is 0.58. And what are the units for velocity?
Meters per second.
Very good. You're a good unit girl. 0.58 meters per second as it passes through equilibrium. Now that's going to be its fastest speed because it sped up to that as it was coming back, but as soon as it passes equilibrium, the spring is going to be pushing back on it, and it's going to start slowing it down.
Okay.
So that is going to be the max velocity as it passes equilibrium. All right, kind of like the pendulum, when the pendulum is swinging back and forth, it's going to have its greatest speed at the bottom.
Okay.
So right at where the potential energy is 0, that's where the kinetic energy is the greatest.
Okay.
Now we have to solve part B as it passes the 7.5 centimeter mark. Now luckily I gave it to you 7.5 centimeters, which is exactly half of 15. So you can already know that it's going to be half potential energy and half kinetic energy because it's halfway in. But, well, let's just work it and see. It's half the distance. No, wait a minute. It's half the distance, but because the distance is squared, see how the x is squared? When things get squared in an equation, it's not like the proportions. If it's half the x, it doesn't mean the total value is half because the x got squared. So you have an exponential equation there, which doesn't work proportionally as easily. Do you remember we said with the ladder thing? If it's half the height's not squared in the MGH equation. See the gravitational potential energy equals MGH at the bottom?
Mm-hmm.
That height isn't squared. So if the height is halfway down, then that means the gravitational potential energy is halfway down. I mean, it's halfway the amount. Because you cut the height in half, then you cut the gravitational potential energy in half. The height's not squared. But in this equation, if the x is squared, think about it this way. If you doubled the x and made x go up by a factor of 2, well, because x got squared, your potential energy is going to go up by a factor of 4 because that x in that equation is squared. If you triple the x and you make x go 3 times greater, your potential energy is going to go 9 times greater because x is squared in that equation. So when you increase x by 3-fold or 3 times greater, you pull it 3 times farther, your potential energy of that spring is going to be 9 times greater because the x got squared in that equation. Does that make sense? So this is called an exponential relationship where it's not linear. The gravitational potential energy, depending on height, that's a linear relationship. Because when one increases, if one increases by 5, the other one increases by 5.
Okay.
5 times. But with this, if x increases by 4, the potential energies are going to increase by 16. Because the 4 gets squared. Okay. Let us do part B as it passes the 7.5 meter mark. I'm simply going to quickly draw the situation one more time. 8 kilograms. It's being pulled out by 15 centimeters, but it's going to come back in 7.5 centimeters, and we have a K of 119 newtons per meter, and we know that's a little bit messy, but we got it. And we know that we have the energy before is going to equal the energy after. You don't have to write that every time once you understand it. Now beforehand, when we stretch it out, let's say we stretch it out nice like that, right, 15 centimeters.
Mm-hmm.
Of these types of energy, potential energy, gravitational, kinetic energy, and potential energy of the spring. These are your 3 types, okay? Beforehand, can you tell me what it has? Because we're going to do the before and the after equation. So we're going to do before and after. What does it have before when we stretch it out and we're about to release it? What does it have?
Okay. It has potential energy.
It does. It has the potential energy with a little s for the spring.
It doesn't have gravitational potential energy.
Right.
And then you're stretching it out so it has kinetic energy.
Yeah, before you release it, does it have kinetic energy?
No.
No, it's just stretched out. So all it has beforehand is the potential energy of the spring before you let go. Okay?
Okay.
Now, after you let go and it's halfway back, so this is afterwards when it's halfway back, what does it have? Okay, so is the spring still pulling or pushing on it when it's halfway back?
Yes.
Okay, therefore, does the spring still have some kind of energy stored in it?
Yes.
Okay, good. So it still has some of the potential energy of the spring.
But it has kinetic energy too.
Exactly. It's got both now, which is why this part is a little bit harder.
Okay.
But it's not that hard, as long as you understand the concept that now it's got both.
Okay.
And if it were up high, it would have all three. So let's do the potential energy of the spring beforehand on the left. What equation? Now we don't see the equations. Can you remember it?
PE, oh gosh, I remember KE. KE is 1/2 mv squared, and then
Woohoo!
PE is, what is it, 1/2 kx squared.
Yeah, you did. I didn't even have to turn the page. 1/2 kx squared is the potential energy of the spring. So we're going to have 1/2 times 119 times 0.15 squared, which is the same as last time. That's how far it got stretched. Now afterwards, what's the potential energy of the spring halfway back? What's this? You know it. It's the same equation.
Okay, but then is it the same like values?
Yeah, different values. So we're going to have 1/2 kx squared, but now the k is still 119.
Mhm.
What's x?
So then the x would be 7.5.
Yeah, and how about 0.075 for meters?
Okay.
Just like 7.5 cents.
Mhm.
Okay. So that's the potential energy of the spring when it's halfway back. Plus, what's this one?
1/2. What was the math? 8.
Yeah, 1/2 mv squared. And we'll go ahead and do 1/2 times 8.
And then v squared.
Yeah, baby. You got it, right?
Mhm.
So what if we get rid of all these 1/2s because they're all over the place? Whoops. All right. We could solve that. No problem. So we'll do 119.15 squared times 119. All right. And then we'll do minus, right? We're going to subtract this.
Mhm.
Oh, did I forget to square the 0.075?
Oh, yeah.
I forgot to square it.
It's okay.
There we go, right there. Okay. So we're going to do minus 119 times 0.075 squared, and luckily our calculators know the order of operations. So I got on the left 2.008.
Hang on, sorry. My mom is calling me.
Okay.
Sorry.
I'm heading out, though. No, later.
I was happy, honestly. Okay, I'm back.
Okay. So 2.008 on the left, and then I get 8v squared on the right, divided by 8. So I get 0.25 equals v squared. We'll do a square root. Are you liking this?
Yeah.
Okay, so I got a velocity halfway back of 0.50 meters per second.
Okay.
Let's go back and see if that even makes sense.
Yeah.
0.58. Yeah, 0.58 is higher, and halfway back is 0.50. Notice that the velocity is not half of 0.58 because here's why. When the spring is stretched at the way, like at way out, when it's really way out, that's when it's going to be pulling the hardest. And the closer and closer this block gets to equilibrium, the less force the spring has on it, because it's not going to be pulling as hard when it's closer to equilibrium. So it doesn't speed up as much during that second half of its trip, and it sped up a lot more during its first half because that spring was really pulling hard when it was stretched way out there.
Okay.
So that's why it sped up to 0.50 in the first half meters per second. But in the second half of the trip, it only sped up another 0.08 meters per second, because that spring really wasn't pulling as hard as it was in the beginning of the trip. Okay, let me give you a couple more formulas.
Okay.
Okay. Work. Oh, by the way, the definition of energy is the ability to do work in science.
Okay.
And work, the definition is when a force moves an object. You have to actually move something through a distance. I guess it's understood that when you move something, you move it through a distance. So you could push on a wall really hard all day long, like a cement wall, and if it never moves, in science, in physics, you could say you never did any work because you never moved the wall, even if you're sweating and you're tired at the end of the day.
Okay.
So you have to actually move an object. So work, the definition is work equals force times distance. So the force you used to move something and the distance it moved. Here's the catch, the tricky thing. The force and the distance must be in the same direction.
Okay.
Or parallel. So they have to be along the same line. Or you could say along the same direction, along the same line. Okay? So it's really easy if you're just pushing something straight, like a box, and you use a force and you move in this direction. There's the force, there's the direction. You just multiply the force times the direction and you get your work. Work is in joules just like energy is in joules. We never even talked about the joule, did we?
No, I don't think so.
We didn't.
Okay.
The units. Let's talk about these units. Okay. The units for kinetic energy, potential energy, and all of that, energy units, is the joule, or the kilojoule. So a joule is a Newton times a meter. In terms of like, what is it equal to in terms of other units? So a joule is a kilogram meter squared per second squared. Not that you need to know either of those, as long as you know that the energy unit for potential energy and kinetic energy is joules. So if you have to answer a question like the kinetic energy equals blah, 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 it's going to be in joules. And the potential energy of a spring equals, and then you'll answer, and then you'll say joules.
Okay.
Okay, so that's the unit. Now work, energy is the ability to do work, and work is also in joules, or kilojoules, and 1,000 joules equals 1 kilojoule. So it's really easy when you just multiply the force, the newtons times the meters, and here's where you get force times distance equals Newton times meters, which equals the joule. So it's really easy when the force and the distance are obviously in the same direction. But he'll give you a problem, and this is not very hard, but he'll give you a problem with a lawnmower or a shopping cart. So if this is the lawnmower and this is the handle, and you're pushing the lawnmower 15 meters, and the force you use is along the handle and it's not in the same direction as the direction you're pushing the lawnmower, but let's say the force is 35 newtons. You can't say work equals 35 times 15 because they're not in the same direction or along the same line.
Okay.
So what you have to do, if he gives you the angle, let's say this is 20 degrees, what you have to do is break apart the components of the 35, and you'll say, okay, this person is pushing down and over. And which one, this is the force perpendicular to the ground, and this is the force parallel to the ground. Which one do we need?
The parallel one?
Yeah, you need the parallel one. So we're going to say cosine, right? We're going to say 35 times cosine of 20, and that will give us the force parallel, because the cosine of 20 equals the adjacent. How are you with your trigonometry?
I'm pretty good.
You're pretty
I
good?
usually don't write out like 35 cosine 20. I just kind of like do it.
You just do it. Okay, great. Yeah. So cosine of 20 is the adjacent side over the hypotenuse. All right, so then we could get the parallel force, and we could do 35 cosine 20, and we get 32.9. So the force parallel is 32.9. So then you could say, oh, well, then the work done is the force times the distance, that parallel force times the distance, which is 32.9 newtons times 15 meters, and you would get the joules.
Okay.
So that's how you do, so 493 joules. Is your teacher, how is your teacher about significant figures?
He does not care at all.
Okay, good. I mean, not good, but good for us right now.
Yeah.
All right. So we have that type of problem, which you have to find the component that's parallel to the motion. Then he's going to add problems where there's friction. So we can do a situation like this where we have an inclined plane. As the box slides down 210 meters along the surface, is that the direction that gravity pulls?
Yes.
What direction does gravity pull? What direction is the force of gravity? Gravity. Think about gravity. Don't think about problems in physics. Just think about your life before you took physics. What direction does gravity pull you?
It keeps you on the earth. So
yeah. So when you fall, what direction does gravity pull you?
Down.
Yes. So gravity is always going to be straight down. That's the direction of gravity. So let's say the force of gravity pulling this box. So the force of gravity in every single physics problem, you have to draw it straight down and not at an angle to the left or the right.
Okay, so you're looking to find the length of the horizontal line?
Yeah, the length of which one? Did you mean horizontal or?
Vertical.
Vertical. Yeah, the vertical. How far did it go vertically?
Okay.
What do you think we should do?
Well, we don't have the full distance. Oh, I guess you don't really need it.
Yeah, tell me what to do.
So you do sine 28 times 210.
Because we could in this distance if we have 28 and 210, right?
Mm-hmm.
So we could figure out how far down it went because this distance is in the same direction as the force of gravity. Yeah. Okay, let's do that. Let's do 28 sine of, or 210 sine of 28. $98.59. Okay. So the distance that it went down is 98.6 meters.
Okay.
Now we could do how much. So now tell me what's the work that gravity did.
98.6 times the force.
Yeah, what is the force?
what was the force equation?
So the force of gravity, think back to your previous chapters. How do you get the force of gravity?
You
know this.
Is it like F equals mg?
Good job. The mass times g is the force of gravity, which is the weight. So the weight of the object is the force of gravity on that object. So we're just going to do 8 times 9.8 because that's mg.
Okay.
Okay? And check this out. Do you think, because this is the distance and this is the mass and this is g, do you think that's kind of the same as mgh? Like the height that it was?
The height.
So now you see that the work done is really similar to the potential energy, the gravitational potential energy change. The change. So the work done, and we'll talk about the work energy theorem next, the work done is often the same as the change in the object's energy.
Okay.
But let's just do force times distance here. The force is mg, which is 8 times 9.8. And then we'll do distance, which is 98.6 meters. So we get 7730. So that's the work that gravity did, 7730. Are we done, or do we need a unit?
We need a unit.
What would that?
That would be, the force is joules. The weight would be...
No, we're doing work. Sorry, W is work.
Oh. The joules?
Yeah, joules, right, because the force was newtons and the work is in joules. Very good.
Okay.
Yep. Okay, so that's the work done by gravity.
Okay.
And the tricky part about that was you had to find the distance that was in the same direction as gravity's force. And you found it. Mm-hmm. And that was the force and that was the distance you could multiply by each other. Okay. So that's a typical problem that will probably be on your test. What was the work done by gravity? Now you could talk about the work done by friction. If, let's just say, let me think about how to do this here. We could say the work done by friction I might need to make the coefficient of kinetic friction a lower number, because at that high of a coefficient, the 0.39 that I gave you, it's possible that the friction would be too high and it might not slide at all. So I'm going to change that number, if you don't mind, just to make sure we have a number that works. And I'm going to make it like 0.19. Okay. Now we're going to say for part B, how much work is done by friction in opposing the motion, as it resists the slide. He's probably not going to say in opposing the slide. He's just going to say how much work is done by friction.
Okay.
All right. You can always draw friction, the force of friction, as an arrow that goes opposite the motion, because friction will always be opposite the motion.
Okay.
So if the box is sliding down 210 meters, you just draw a vector labeled FF for force of friction, and that's going to be opposite the direction of the motion. Now, do you remember the equation for the force of friction?
Is it like mu n?
Yeah, very good. So the force of friction equals mu times the normal force.
Okay.
So let's calculate that, because we need to know, in order to get the work done by friction, we're going to need the force of friction times the distance.
Okay.
Okay, so we'll say we know the mu is 0.19. Now the normal force. Do you remember how to get to normal force?
Oh, gosh. Is it just F equals mg?
No, that's going to be the weight, which is straight down. And sometimes the normal force is straight down, but I'll show you that example in a minute. The normal force is the force perpendicular to the surface. So normal in physics means perpendicular.
Okay.
So the normal force is always perpendicular to the surface. So check this out. Look at the 8-kilogram block. The normal force is going to be pushing on the surface because you can imagine that the block is pushing on the surface a little bit, and it's also wanting to slide down the surface. And so the weight, which is the orange vector, the FG, is made up of two components. The weight causes the block to push on the surface, which is the normal force, and the weight also causes the block to want to slide down the surface, and I call that the parallel force because it's parallel to the surface.
Okay.
So there's two parts, two components to the weight of the block. And the normal force is the one we need when we're dealing with friction. So let's calculate the normal force. And by the way, if the 28 degrees is right here, then we also know that this angle right in here is 28 degrees.
Okay.
I'm going to try to put a 28 in there. All right, so we've got 28 degrees, so we'll have cosine of 28. And what is the hypotenuse of this triangle? What number?
210.
It would be, very good point, it would be on the distance triangle. So on the distance triangle, we had the hypotenuse as 210, right?
Mm-hmm.
But in this triangle right up here,
The smaller one.
it's a force triangle, not a distance triangle, and the force of gravity, or the weight of the object, is the hypotenuse. Did we figure out the weight of the object? We did 8 times 9.8, but I don't think we ever, let's do 8 times 9.8. So 78.4. So this is 78.4 newtons, and that is the weight of the object, and that's the hypotenuse of the force triangle.
Wait, but why?
Because FG, you see the 8 kilograms?
Mm-hmm.
So the 8 kilograms is, the 8 is the mass, and mg is 8 times 9.8, and that's the weight of the object, and that's 78.4 newtons.
But, why is that your hypotenuse?
Good. Okay. When you draw an object on an inclined plane, I'll just go to the next page, and then we'll come back. Whenever you draw an object on an inclined plane, you're going to draw the object, and you're going to first start by drawing the object's weight going straight down. And then you're going to draw the normal force, and you want to draw, imagine in your mind this dotted line that's parallel to the surface. And you're going to draw a normal force which is perpendicular to the surface. This is like a pattern of what you do when you have inclined planes. And then you're going to draw a parallel force. So this is your normal force. This is your parallel force. And this is your weight of the object, or FG, which is mg. So whenever they give you, in every problem, whenever they give you the mass, let's say this is 10 kilograms. That box is 10 kilograms. So because the weight, which is considered mg, right, or FG, is 10 times 9.8, which is 98 newtons. The hypotenuse of that triangle is 98 newtons. So that's going to be 98 newtons on that hypotenuse because you've just drawn a force triangle. Now the weight goes straight down because gravity pulls straight down, so that's an N right there, 98 newtons, pulling straight down, and I can also put it down at the end of the vector. We've got 98 newtons as the hypotenuse because that hypotenuse goes straight down. And then look, see how it's broken down? The weight does two things. The weight of the box is the hypotenuse, right? And the hypotenuse is like the resultant in this case.
Yes.
Now, it has two components, or parts. It has the normal force and that pushes on the surface, perpendicular to the surface. And would you agree that the weight causes it to push perpendicular to the surface? Like it causes it to push on the surface to some extent.
Yes.
And then the second component is the parallel force, which makes it want to slide down. So the weight does these two things. Now these two together make up the weight of the box, just like when you add vectors, this plus this makes this.
Okay.
So the normal force and the parallel force, the normal force and the parallel force together make the weight of the box when you add vectors. And the weight, again, is that hypotenuse always. On these inclined plane problems, the weight will always be that hypotenuse. And always, this angle in here, whatever theta this is, this angle in here will be the same because they are congruent triangles. And that was hard to read, but I'll try to do it.
Okay.
That's theta right there.
Okay.
All right, back up here. Now you understand that the weight is the 78.4, which is the hypotenuse on that force triangle that we've drawn. We got a distance triangle congruent to a force triangle.
Okay.
So now, where were we? What are we trying to find? The friction. Okay. So we found 78.4. Can we get the normal force? Did we get that yet?
No.
Let's do that. Let's do cosine of 28 times 78.4. Do you like that?
Yes.
So the normal force I found to be 69.22.
Okay, and then you multiply it by 0.19.
Yep. So we'll do times 0.19, 13.15. So I'm going to say the force of friction equals 13.15 newtons. It feels like we're done because we did a gazillion million things, but they didn't ask for the force of friction. They asked for the work done by friction.
Okay.
Would you agree that the force of friction is in the opposite direction as the motion?
Yes.
Okay. So your teacher probably wants you to go like this. He probably wants you to put a negative on that force of friction to show that it's in the opposite direction as the distance, which is going to be in a positive direction. It doesn't matter which one you call positive and which one you call negative. Some people want to call the down one negative and the up one positive, but usually we want to call friction negative because it's opposing the motion. And it's doing, if the gravity is doing positive work by pulling this object down, we're actually going to say that friction is doing negative work. Not that it's doing less than zero, it's just doing work in the opposite direction, or in a different direction than the motion.
Okay.
So we're going to say the work done by friction is work equals force of friction times distance. So the work done is going to be that negative 13.15 newtons.
Times 210.
Yeah, 210 is how far it went.
Okay.
All right, let's multiply by 210. 2762. And what's the unit?
Joules.
Good job. So that's the work done by friction. Oh, make it negative. Negative 2,762 joules if your teacher doesn't care about significant figures. If your teacher does care about significant figures, then in this problem with two significant figures, 8 kilograms has 1, so you would round it to 3,000 joules. If you were allowed two significant figures, you would just say 2,800 joules.
Got it.
You got it. Okay, so we did some good problems. You know now that work equals force times distance, and you know kinetic energy equals 1/2 mv squared.
Yes.
And you know that the potential energy stored in the spring is 1/2 kx squared. And you know that gravitational potential energy is mgh. And you know that the force of a spring, Hooke's law, states negative kx is equal to the force of a spring pulling or pushing opposite of the direction of whatever direction you pull or push the spring. And you know that the units for work and energy are joules. And you know the law of conservation of energy, that before and after an event, the energy will be the same. Now, this is when you have 100% efficiency, but in later chapters, you're actually going to learn how some of that energy is lost as heat. And so you could have something like an engine or something converting potential energy into kinetic energy, like gasoline into the motion of a car. But some of that energy from the gasoline is going to be converted into heat due to friction in the engine, and you're going to have an engine that's less than 100% efficient. And so, it's going to look like the energy you get out of that machine is less than the energy you put in, but that's going to be when you do machines. Okay, really quickly, just because I hate to finish this without telling you two very important equations. And the work-energy theorem states that the work done is equal to the change in energy of the object. Now, this is going to be a shortcut sometimes in the problems, because sometimes you'll be working really hard on these friction things, and you'll be figuring out the force and the distance, and all this force and distance stuff, and you'll be like, okay, work is force times distance, and you'll be racking your brain, right? And other problems, you're just going to figure out the change in energy of the object. For example, if an object falls from 10 meters down to 0 meters and it had a mass of 10 kilograms, you could say 10 times 10 times 9.8, so 980 joules, right? That was the change in its kinetic energy, because it was like up here it was mgh and down there it was 0. So you could say, the work done was just the change in its energy. So that's going to be a nice shortcut that you can use sometimes. And this will work also when you say how much work was done. If you throw a ball and you give it, let's say you give a ball 150 joules of kinetic energy. Let's say that's given to a ball. How much work did you do to give it that much kinetic energy? Well, the work done, therefore, was 150 joules. Okay. Because you gave it, that's an exclamation mark, because you gave it 150 joules of kinetic energy, therefore you must have done 150 joules of work to change the ball's energy by 150 joules. Okay. So this is a really easy, quick equation, and sometimes on problems this will save you a lot of time. Okay. And then the last thing I want to tell you is, oh dear, there's two equations I still want to tell you really fast. Power is work done divided by the time it took. Okay. So power is in joules per second. Oops, I spelled joules wrong. Joules per second. And a joule per second is called a watt. Now a watt is like a 100-watt light bulb. So a 100-watt light bulb gives you 100 joules every second of energy. Gives you 100 joules of energy every second. Okay. So power is in watts. So you don't say joules per second. Now you'll just say watts. Okay. But it's the rate. So think about this. You know when you divide things by time, like how much time it took? So whenever you divide by time, whenever you divide by time, that equals a rate. Okay. So power is the rate of doing work. How fast you're doing it. Okay. Or you could say the rate of transfer of energy. So it's either the rate of doing work or the rate of transferring energy. You with me so far? It's how fast the work is done.
Okay.
Okay. So that's the work. So you could say power equals work over time, or you could say power equals change in energy over time. But the time has to be in seconds.
Okay.
You can't have the time in minutes.
Okay.
In physics, time in all these equations is always in seconds, nothing else.
Got it.
Got it? And now you're ready for the very last equation. I told you there were two more, and there's just one more left, okay? So, you know how work is force times distance?
Yes.
Okay, if we have power equals work over time, do you agree that that means force times distance over time?
Yes.
And would you also agree that distance divided by time is velocity?
Mhm.
You remember that?
Yes.
So would you be okay saying that power equals force times velocity?
Yes.
Distance over time is velocity.
Mhm.
And you're good.
Okay.
All right. Do well, and
Thank you.
let me know when you need me again.
Okay. Thank you.
All right. You're welcome. Bye-bye.